start recording. So last time we did this, got to this expression where we talked about the potential difference was equal to minus G, big M, little m, 1 over R final minus 1 over R initial. And the negative sign is there just to make, you know, because you're considering a mass that's isolated, then my negative sign is there to make the sign work out right. If I'm going further away from a mass, it's like going downhill on a volcano. And so my change in potential difference is a negative value as I go from close by to far away. And if I'm close by, then this number is relatively big. And if I'm far away, then that number is relatively small. And so that means that comes out to be a positive value. And so I need the sign there to make it into a negative. Okay. So let's do this problem. So can you have a go at that, please?
So this one we're plugging in.
So hopefully I had a crack at that. And basically what we did was we wrote down our equation. Delta U is equal to minus G, big M, little m, 1 over RF minus 1 over Ri. And the big M is pretty obvious, it's 80. And the little m is pretty obvious, it's 5. And then these RF and RI, and it's kind of helpful to look at a diagram. If we don't have a diagram, we need to draw one. But if you look at this, this is clearly 8 units long. There's no X, there's no Y and no Z component here. And this is clearly 2 units long. So whatever I take, I need to find my magnitude from my mass to my point of from my mass to my final position, and from my parent mass to my initial position. I substitute the numbers in, work the handle, I get an answer, and I go, it's 150. I left G in here because I just don't want to mess with it. Yes?
Would it work if you just minus you subtract both of the vector, right?
I'm sorry?
If you subtract both of the vectors, so it would be like 8 minus 0 and 0 minus 2, right?
So, and do what with it?
RF minus R initial, right?
Well, I want 1 over RF and 1 over R initial.
Yeah, that's what I meant. But wouldn't it be negative 2 because you're doing 0 minus 2 for the second one?
That's that RI and the RF are distances. So the magnitudes. Yeah, the magnitudes. But try it. I mean, you can try it that way and see if you get the same numerical value. I think so. And I've got to revisit something because I said the negative sign was there to. And as I'm sitting here, I'm thinking about this negative sign. This is a positive value. And if I think about it, so I need to do some talking about that. And here's the problem. The problem is that we don't know where the lowest point in the universe is. So we can't have 0 potential energy at the lowest point in the universe and count upwards. So what we do is we go to the most distant point in the universe from any masses and we count downwards. So this is 0 joules, way off in infinity. And then here's the top of my mountain, here's the bottom of my mountain. So let's say, I'm going to quickly make up some numbers here. So let's say that this was, this would be minus 6 joules, and this would be minus 12 joules. Okay? If I go from there to there, I've gone, my delta U equals minus 12 minus 6. So that equals plus, that equals minus, sorry, that's minus 6 joules. So I got a problem. I need to think about it because I have a negative sign here when I should be having a positive sign.
That should be negative 15 if it's negative 12 minus 6.
Minus 12 minus 6.
That's plus minus 6.
I know, but I meant minus 6 is going to be minus 6. So just bear with me on the sign. I'm like, I dug a hole for myself. And I need to work it out. And I'll get back to you on it, okay? So I'm just doing something silly in my head. So, next. And this is not so often talked about, and that is, I want to work out the actual number for these guys. I want to work out these values. I don't want to just deal in terms of the difference. I want to work out these values. So I want to have proper numbers for that. And so how can I get proper numbers for that? And the way I get proper numbers for that is I kind of, well, I don't cheat, but I kind of recognize the fact that I do put 0 joules infinitely far away from all the masses. So my graph of potential energy versus position is basically 0 is infinitely far away. I can't get it on my paper, but it's way over there. So infinitely far away, I have 0. And then as I approach, I get a lower and lower potential. Okay. Oh, yes, I'm sorry. Let's step back. Duh. I've got to go back to here. I need to think about it. I just put my mass as a mountain and put my other mass as a boulder and had the boulder rolling away from the mountain, which does not happen. It does with mountains, but not with planets. You don't get repelled from Earth, you get attracted to Earth. So my analogy is awful. It's exactly the wrong analogy. What I need to do is I need to stop thinking about that, and I want to go to the golf course and think about that. This is what the analogy is for gravity. Planets attract, so they're at the bottom of a potential well. They're not on the top of the mountain, they're at the bottom of a sinkhole. That's what a planet is. Now, when I think about it, my R initial is here, a long way away, and my R final is there, nearby. Let's have a look. And if, oh, sorry, no, I got that backwards. My R final is a long way away, and my R initial is nearby. And if I have my U final is a bigger negative, is a higher position, and my U initial is a lower position. So this might be -3 joules, and this might be -7 joules, because it's lower down. Does that all make sense so far? We're deciding to have 0 joules infinitely far away, and masses attract. So as I get closer and closer to the mass, I have a more negative number, but rather than going from a zillion to 0, I have -3 to -7. -7 is a more negative number than -3, so that's all making sense. And my difference, my U final minus U initial, my delta U, is equal to -7, -3 minus -7, which equals +4 joules. So in going away from a planet, my change in potential energy should be a positive value. And that makes sense. If I lift something in the air, the change in potential is positive, yeah? So it makes sense. So ignore all that about, we'll get back to this in physics too, when we have positive charges and negative charges, and we'll have volcanoes and sinkholes to deal with. But at the moment, we're only picturing sinkholes, okay? So that's why this answer works out to be positive, because we're going from a point that is there, that's my 2, The direction doesn't matter. It's just how far it is away. Agreed? The direction doesn't matter. You can think of it as a whole bunch of contour lines. It's just I go from a point there which is a little bit away to a point there which is a lot further away. And so my change in potential energy is a positive value. Okay? Make sense? If I dug myself out of the hole? Climbed out of the hole, I should say. Okay. So now let's go on to the next bit. And now we're going to say, okay, listen. I want to find the actual numerical value for the potential energy at that point. Don't want a difference. I want the true value. So how do I work it out? And I say, well, man, if it was the difference I wanted, I could figure it out because I have an equation for that. Oh, let's make the difference between 0 and my value. If I want to know the true height, I say, what's the difference between 0 and my height? Then it's not a difference in height, it's the value for the height, yeah? So, what I do is I say, oh, look at this. G, M1, M2, 1 over RF minus 1 over R initial. And I imagine moving my second mass from infinity. So that becomes 1 over infinity. Because it's infinitely far away. And what is 1 over infinity?
0.
So that term goes away. So I get that term. So you want to know the actual value for the gravitational potential at a given point? Sorry, the gravitational potential energy. How much potential energy does that mass have because of its proximity to the parent mass? You just work that out. Minus G, big M, little m, 1 over R. I don't particularly remember this one. I know that one. And I go, oh yeah, I want to find the actual value. I just put 1 over infinity in and I'm done. So I know how you get from this one to this one very comfortably. So I don't bother learning this second one. I kind of know the first one very well. You might want to learn both, or you might want to do the same thing that I do. Learn one of them, figure out how to get the other. You know. So an 80 kilogram mass is located at the origin. And determine the potential energy of a 5 kilogram mass when it is located at 0, 2. So this is 5 kilogram, and this is 80 kilogram, and this is 2 meters. So I would say, oh well, my change in potential is equal to minus G, big M, little m, 1 over R final minus 1 over R initial. So I know from that that my U, not my delta U, my U is equal to minus G, big M, little m, 1 over R. So I go, that equals minus G, big M is 80, little m is 5, 1 over 2. U is equal to 5/8 of 40, that's 400 over 2 is 200 G joules. So minus 200 G joules. I'm testing there to see you're comfortable with the signs. Minus 200 G joules. How can you have a negative energy? It's just a number scale. It's just a ruler, and we don't know where to start it if we go to the lowest point, so we start it at the highest point. That people feel uncomfortable with that. So if you feel uncomfortable, don't be worried about it, but just try and get comfortable with it. Okay? It's like I have a point here. I could try and measure from the ground upwards, or I could go infinitely far away and measure downwards, and that's what we do. Rather than calling the bottom 0, we call the top 0, and we work downwards. I think it's familiarity. Little bit more interesting. So a 70 kilogram mass is located at that point. What is the gravitational potential of a 5 kilogram mass located at that point? Ooh. So let's just do one of these. No attempt to actually draw it correctly. I'm just going to say this is 70. And this here, I'm going to draw it down the side. This is going to be 2i plus 3j plus 1k meters. Amazing. It's just, remember practicing to put your units in after you've had an IJK. People sometimes miss it. And this is the 5 kilograms. And this is 3i plus 2j plus 4k meters. And I want to find the gravitational potential energy. I want U here, okay? So I remember that delta U is equal to minus G, big M, little m, 1 over R final minus 1 over R initial. And so that reminds me that U is equal to minus G, big M, little m, 1 over R final, I can call it 1 over R final. Where am I? Yes?
But if it's asking for the just gravitational potential energy, are we just using the 1 over R then?
That's what I've just wrote down. Yeah, it's 1 over R.
Oh, okay.
Yeah. As I said, I tend to remember the first one, and I can always figure out the second one. Okay? So then I say, okay. Not a vector in sight, by the way, so I don't need to worry about, do I need the thing? Well, I will, but not this minute. So let's put in what we can. Minus G, big M is 70 in this case. Little m is 5 over R. And my R is there. Okay. I need to figure this out. I do need vectors. Doesn't matter which way around I do this. I'm gonna say that this is R1. I'm going to say this is R2. I'm going to say this is R3. I want R1. Now think back. Look at the arrows on these things. If you were drawing this as a vector diagram, which would be the resultant? And which two are you adding together? Resultant is the single vector, which starts at the beginning of your first vector and ends at the end of your last vector.
R2 plus R1.
So which is your resultant?
Oh, the result's R3.
Resultant is the R3 because it begins at the beginning of this first vector and it ends at the end of the last vector. So that's my resultant. So R3 is my resultant. And how did I get that? I added these two vectors together. So I said that equals R1 plus R2. That's the equation that describes that diagram. Agreed? Agreed? So, what do I want to find? R1. R1 is equal to R3 minus R2. Agreed? Yep. So let's put down R3. R3 I actually, I'm sorry. R3 actually no. Let's do I, J, and K. And I'm going to go 2, 3, 1. And I want to subtract from that. So this is my R3. I want to subtract from that, going to this, my R2. Well, there's my R2. Where I subtract is, I just add the negative of. So I can have minus 3, minus 2, minus 4, I can just add those up. I get -1, +1, -3. Did I do that right? So this is my R1 vector. I don't want the vector. I want the magnitude of this vector. So R1 mag equals the square root of -1 squared plus +1 squared plus -3 squared. So R mag is equal to the square root. 1 plus 1 is 2. 2 plus 9 is 11. So U is equal to -G 70 times 5 over square root of 11. So if I get my handy-dandy little calculator, I'm going to get 350 divided by second square root 11. I'm getting 105.5 minus 105.5 big G joules. 106. The answer is C. Cool. So it's the same principle. I just made it a bit harder to get to. But it's the same principle. Agreed? So don't forget about your vector stuff just because we haven't done the vector chapter in a while. Okay, just make sure that you can get a magnitude, you could find the unit vector, you can draw a vector diagram, and you can figure out this skill about, if you don't draw the diagram, I don't see how you can do that problem unless you've got a brain that is far more capable than mine. You know, I can't tell you what the equation is linking R1, R2, and R3 without the diagram. I can't even visualize R1, R2, and R3 without the diagram. So it's not a hard skill. You can do it. It's just if you're not thinking about it, you'll kind of go, I don't know how to begin. So just don't let that happen. Just go on with it. Last little bit. So we had the gravitational force, and we said, you know, I kind of like this idea about being more abstract and more general. So I went to my gravitational field, which is little g. I know it's like little ladder. We should expect it to be a big ladder, but it's a little ladder. And I got that by saying it's Fg over m. So this is field. This is force. This is a really useful little diagram, by the way. And then we used the gravitational force and we multiplied it by a distance. And I got my gravitational potential, energy, gravitational potential energy. So this is pot energy. And we kind of did it. It was a variable force. So we kind of did it by saying that our energy equals our work done, which equals the integral of fx dx. That's kind of how we did it, just by the by. And that's that equation. That's that 1 over r final minus 1 over r initial. Yeah. So then I'm also going to find it useful to get a bit abstract, and I'm going to say Ug over m is equal to Vg, and this is the potential. If you like, the gravitational potential. And the gravitational potential is the energy per kilogram. Let's say I went to the moon. I want to climb a mountain. You could tell me how high it is. Doesn't help me much because different gravity, so it's hard for me to interpret it. You could tell me how much energy I would need to get to the top, which works for me, but it's not going to work for somebody else because they got a different amount of mass. So it's better to characterize the work done in climbing mountains on the moon in terms of the gravitational potential energy per kilogram. So I go, oh, I'm 80 kilograms. I've got to multiply that energy by 80 and figure out how much work I'm going to have to do. You're 60 kilograms. You've got to multiply that answer by 60 to figure out how much work you have to do. So again, it's going back to this idea about fields are great for, like maps. They're great for everybody. Potentials are great for everybody. Forces work for you and me. Potential energy works for you and me, but it's not generalizable easily. But a field is, and a potential is. Unfortunately, they didn't give it a fancy name. It's very similar to potential energy. So it's easy to get confused. Sometimes when you're talking, you'll say potential when you mean potential energy. So you've got to distinguish them in your mind. And what also makes it interesting is we have potential energy difference, and then we had potential energy, and now we have potential, and I can talk about potential difference as well. So there's a bit going on here. But it's just the potential energy divided by the mass, the little mass. And by the way, when you go to a store and you buy a battery, you're defining that battery in terms of its electrical potential difference. So when you're talking volts, you're talking not about potential energy, but potential. It's the energy divided by the charge. So we're used to dealing with potentials. We just don't. Not in this context, you know. And by the way, if I want to get from there to there, how do you think, looking at the symmetries, how do you think I'd get from there to there? What do you think I'd do? If I gave you I wouldn't do this, but if I gave you the G and said, oh, by the way, I wonder what the potential is, you'd integrate it with respect to the position. Because it's nice and symmetrical. You want to go from left to right, you divide by mass. You want to go from top to bottom, you integrate with respect to distance. You want to go from right to left, you multiply by mass. You want to go from bottom to top, you differentiate with respect to position. It's nice and symmetrical. So a little diagram like that, just word to the wise, little diagram like that, not really going to help us much at the moment, but a little diagram like that in physics 2, when we're talking about electrical stuff, is a savior. It's a lifeboat. Because you can figure out how you work your way around very easily without remembering 6 equations that are similar enough and different enough that it's easy to get them confused and get no marks for it. Okay, so watch out for that. So what do we do? Well, we just take, let's have a look. I knew that delta U was equal to minus G, big M, little m, 1 over R final minus 1 over R initial. Do you think I know that equation because I keep writing it down? If I didn't know it at the beginning, I know it now. And that was enabled me to figure out that U was equal to Gm, little m, 1 over R. And now I know, oh yeah, well, V is equal to U over M, which equals minus G M 1 over R. I don't remember a whole bunch of equations. I just figure out how do you hop from one to the other to the other. It's like walking around a mall. You know, I'm opposite Burdines. I go left and the pizza place is there. You know, I don't know the address of every store in the mall, do I? They're not independently learned. I know the relationships, and that's how I navigate. You can do the same with equations. You don't have to learn every equation. Learn the navigation from key equations. Makes life much simpler. Cool? Let's do it. A 3.6 kilogram block has a gravitational potential energy. So U is equal to minus 43.7 joules, and my M is equal to 3.6 kilograms. Here's my block, and here's my planet, if you like. When located near planet Zebron, What's the magnitude of the gravitational potential? Oh, my gravitational potential equals my gravitational potential energy divided by my mass, which equals minus 43.7 over 3.6, which equals 43.7 divided by 3.6 equals 12.1, 12.2, yeah, 12, well, 12.2 is the closest. 12.2 joules per kilogram. Look at the units. That's the bad thing about multiple choice. Look at the units, you know how to do the problem. It's like,
But why isn't it a negative?
why is it not a negative? It should be a negative. Yeah, good thinking. Oh, what is the magnitude? The magnitude gets you out of a sign. So V mag is equal to 12.2 joules per kilogram. Isn't that, didn't we do a problem just like that when we had electric field and we said, we said gravitational field was equal to the Fg over m. Isn't it the same kind of principle? The math is not hard. It's just the contextualization of it. A 60 kilogram mass is located at the origin. What is the potential at a point located 5 meters away? So I can't use that expression, my potential equals my potential energy over m, because I don't know what the potential energy is. So, okay, let's have a look. Let's remind myself. I said delta U was equal to minus G big M little m 1 over R final minus 1 over R initial. And then I said U is equal to minus G M M 1 over R. And then I said V was equal to minus G M over R, because we divide by the mass. So minus G M, good old M, was 60. And my separation, 5, which equals minus 12 G joules. There. So none of this is mathematically hard. It's multiplication, division, addition, subtraction. That people find it hard. And they find it hard because they're very unfamiliar with the language. So I would like you to be able to know what the different things truly mean. And a big help are the units. Remember what I said? The problem with the multiple choice is that once you've seen the units, you know how to do it. Sorry, is there a question? It's like, I'm getting... Pardon? No? Okay. So there's... look at the units. So for gravitational force, we had newtons. For gravitational field, we have newtons per kilogram. For potential, difference in potential energy, we have joules. For potential, we have joules. For potential energy, we have joules. For gravitational potential, we have joules per kilogram. So those will guide you, you know. Those will give you a good hint of what to do. Then the next thing is put down Fg is equal to big G, big M, little m over R squared. And put down G is equal to big G, big M over R squared. And put down U is equal to big G, big M, little m over R, and then put down V, and that equals big G, big M over R. So when I joined USF, after having taught for a bunch of years, when I joined HCC, having taught for a bunch of years, they wanted me to do a teacher training class. I got a degree in teacher training, so it was like, oh man. I had to go to USF and spend a summer doing this class, and I did it with a particular individual who I knew to be a very much a kind of hands-on, kind of teacher. He was famous for lecturing about not being able to lecture. That was his, And so I thought, this is going to be a disaster. And I went, and it was like the best course I ever did. Because I saw that the guy is really, really good. This guy called Jim Ison is really good. He could do a 4-hour class. We had 4-hour classes. And he would get us to talk, and somebody would say something, and I'd see his eyebrow would kind of like. And at the end of the 4 hours, he'd point back to this person and say, doesn't this just underscore what he said? And you go, yeah, man. So we spent 4 hours recognizing that what somebody said at the first minute was right, which is kind of like, low density in a way. But the intellectual process was amazing. It's teaching skills of thinking. It's really quite valid. And he did it the first week, and I thought, he went and talked to the guy and planted the question, planted the answer. Did it the second week, and it was like, all right, so he's got a bunch of people, a couple of friends, Every week, it was somebody, and he brought it back down. The guy was amazing. As part of our course, we're talking about a thing called critical thinking, which is basically being able to pull up things apart. And one of the hallmarks of critical thinking is problem solving. And every physics instructor I know just about, when we're on these educational committees, say, oh, we do critical thinking because, it's identified by problem solving, and we do problems. Back of the book is full of problems. And I said to Jim Ison, I said, look, just because you call it a problem doesn't mean to say you're really problem solving. It's like we kind of learn how to do these problems. It's not like we're creating a thing. So I don't think it's really critical thinking. So how can I really tell if I am critically thinking? And he said, you compare and contrast. That's a really good hallmark. And it was like this light bulb going off in my head, because I'd been complaining to my wife that in physics 2, people die when we get to electric force, electric field, electric potential energy, and electric potential. They're different chapters, and they use the wrong equation on the wrong question, and it's so frustrating. And I said to my wife, these guys are still not getting it. And my wife said, no, they're new every semester. You're still not teaching it. My wife's pretty hard sometimes, but she's right, And when Jim said that, it was like, I've never put them down side by side and said to my class, let's compare them. So this is in prep for this, because it applies to this as well. Look at the top row. It's to do with force and field. Both of them are inverse square relationships. If I double my separation, I get a quarter the effect. Yeah. Separation between the two masses, separation between the point and the mass. If I double that separation, I get a quarter the effect. If you look at the bottom two, it's about energy and energy per unit mass. And if I double my separation, I get half the effect. So they're behaving different. The symmetries are different. And then look at the vertical rows. If I look at the left-hand vertical column, 2 masses are involved. You want a force, you need 2 masses. You want potential energy, you need 2 masses. Look at the right hand. The right hand, only mass is involved. You want a field? Hey, a mass can set up a field. You want a potential? A mass can cause a potential. So when you see them down side by side, I think you'll make fewer mistakes. So that's my advice. Just live with these for a while. Mathematically, they're not hard. But it's like new language, new equations, new stuff, all coming at once. And it's all similar enough that the equations kind of look the same, but they're not. So it's this awful situation where it's easy to get confused on these. So don't do it. These are going to be on the test, or so part of it's going to be on the test anyway. So make sure you get the points for it. Final bit, escape speed. Escape speed, we have basically, I want to know how much velocity I need to give to my ball so I can kick it away from Earth's gravitational pull. I want to kick it, and I want this thing never to come back. This is not what we worry about with the shuttle, with SpaceX. SpaceX, first of all, is not a projectile, so it's got a continuous acceleration as the flight goes on until it runs out of fuel. And secondly, it's not trying to escape the Earth's gravitational field, it's just trying to get into orbit. So this is truly trying to get away from the Earth's gravitational field.
Is that mechanical energy?
Yes, I'll get to that. No, that's the mass of the Earth.
Oh,
So,
massive Earth.
if you look at my diagram, I'm envisaging starting off at a certain altitude above the center of the Earth, where the ground is. It's not zero, it's 3,000, 4,000 miles above the center of the Earth. And then I'm going to go to a certain height such that, and I'm going to take the kind of the interesting case where I don't get free and have enough energy left over I can fly around forever. I just want to be free so that when I am free, I got no kinetic energy left over. I want the minimum escape velocity. So if I give it more than this value, not only would I be free, but I'd be traveling through space when I'm free. In this one, and I'm free, but I don't go anywhere. And if I had a little bit less velocity, I wouldn't quite make it. So I'm trying to find that cusp between the two. So my final velocity is going to be 0 at this height. And what I say is, well, look at it from an energy point of view. My potential energy at the start, my kinetic energy at the start plus my gravitational potential energy at the start equals my kinetic energy at the end plus my gravitational potential energy at the end. That's just mechanics. And so I have a half mv initial squared plus my potential energy at the start, and because I'm not starting from the center of the Earth, this is not 0. It's g big M little m over RE from my previous equation. This is basically just saying that my U is equal to minus g m over R, which we just did. And then at the end, I got no kinetic energy, but I do have this gravitational potential again. It's just different values. It's the same mass. It's the same mass of ball that I'm kicking. There's just a different distance. Rather than the radius of the Earth, we have from the middle of the Earth to how high I have to go. Rearranging v squared, just finding my v squared. V squared is equal to 2g me 1 over re minus 1 over r max. And of course, this we can take as being infinitely far away. So, goes away. So I end up with this basically. V squared equals 2g me over re. And so when I do the magic to it and do the square root, I get that. I'd like you to know that that's there. I'd like you to know what the symbols stand for if I was to give it to you. So I don't want you to learn it. I don't think they've got enough equations to learn. There's more important things in this chapter I want you to focus on. But I don't want you to blow it off either. So I want you to recognize that ME is the mass of the Earth, and RE is the radius of the Earth, and G is our universal gravitational constant. And there is an equation out there that works. That's all I want. Okay? Questions?
No.
Okay. And there we have it. So let's stop.